Science progresses rapidly, but there's one area of fundamental physics that has been stagnating for almost 60 years. I'm talking about the field of quantum gravity. Quantum gravity attempts to unify general relativity and quantum mechanics, the two pillars of fundamental physics. However, these two theories are incompatible from the very foundations, and any attempt to unify them so far has been fruitless. Today, we're going to see how this failure can tell us something new and unexpected about the universe. Let's talk about space and time. The current idea of space-time has undergone many changes to get to where it's now. It all started from Newton, who came up with the idea of space as an absolute container in which things are. This was later upgraded by Einstein, who talked about space-time, but the real change came with general relativity in 1915. Now space-time is a dynamic entity that can react and interact with the matter inside it. The two theories work very well in their own regimes, small scales for quantum mechanics and large cosmological scales for general relativity. But when you bring the two of them together, weird things happen. One of the weirdest things is the emergence of the Planck scale. This is somehow the smallest scale that can be probed. Anything smaller than a Planck scale cannot be detected, because to detect it, one would need somehow a photon that is so energetic that when confined in such a small region, it will create a black hole. In the 1970s, Stephen Hawking proved that black holes have entropy. But entropy is the measure of how many configurations a system can have, and black holes shouldn't have any. There's a theorem in classical general relativity that says that a black hole has no hair. You can only identify it by its mass, and all black holes of the same mass are the same. This result seems to be very profound. It seems that we stumbled upon a hint that space is not continuous. Think about fluid dynamics. Fluid dynamics uses continuous equations, but it's really describing atoms and molecules. Space-time might not be continuous. It might be the emergent result of some more fundamental and underlying structure that gives rise to quantum mechanics on the small scale and general relativity on the large scale. And so our incompatible theories are only there because we're looking at a very limited portion of the universe and trying to come up with a set of rules that can describe it, but we're not looking at the bigger picture. There are some theories, such as causal set theory or loop quantum gravity, that try to incorporate this idea of a granular structure of the universe and try to look for this fundamental structure. The hope is that future development will once more revolutionize our view of space-time and of the universe.